to see this. So hello everyone and welcome to the Munich virtual meetup here in online. This meeting will be recorded and we plan to put it on YouTube later for other interested people to watch it. For today's meeting, we have actually an interesting talk from Andreas. He will talk about an authentic token IC based on the OpenTitan project. Andreas is working for Fraunhofer, the security department. He also has been traveling worldwide, like having been in Asia and also in different universities in Europe. Later, I also will give a short overview about RISC-V and why it goes big. And before we are starting, I also want to give some updates about the RISC-V, what has changed, what is kind of new, and how the RISC-V International is right now. For this RISC-V meetup here, thank you very much for joining again. If you have an interesting talk, we welcome you to have a talk. Feel free to write me an email, florian@andestech.com. If you have a talk, I hope we can have another meeting maybe in the next 3 or 4 months, maybe even an in-person meeting. So if you have some cool project, if you have something you want to share about RISC-V, please come in contact with us. Okay, before we hand over to Andreas, I would like to give some updates what is happening in RISC-V. RISC-V, we believe we are changing how IC design is done. So we are welcoming everyone to join this innovative, free and open instruction set architecture, which is driven through open collaboration, which is enabling this freedom of design across domains and industry, and which we believe is cementing the strategy foundation of the semiconductor market for the future. RISC-V, we have some updates. So started in 2015. It is now moved to Switzerland. That was happening in 2019, as you may know. There are over 2,000 members in the RISC-V, and we are spanning over 70 countries worldwide. The RISC-V adoption is really accelerating, so it is spanning now really everything. It is going from the data center down to the edge computing. You can find it in telecom and communications. You find it in everything with AI and machine learning. It starts coming into automotive. There are a lot of companies working on this, which is really cool. So your future car might have RISC-V, and it's already here in consumers and IoT devices. So the adoption of RISC-V is really not a single case somewhere in AI or something. It's really spanning every industry and coming into every kind of IC which is on the market today. RISC-V is also changing how we are doing IC design. I personally think that is a little similar like what Linux has done for the software. What we are seeing, for example, Gartner has already said this in 2020, said RISC-V is creating more and more ASICs, so more and more companies have the opportunity and using this to make their own ASIC based on RISC-V. And we are seeing that the ASICs, custom-specific ICs, are growing. So that is another trend which is also accelerated by RISC-V. RISC-V has great process in the industry. So there are a lot of different initiatives who are working on RISC-V. For example, in Europe, we have the European Processor Initiative. There is a RISC-V accelerator architecture under development. There are already test chips back last year, which is really cool. It's based on RISC-V. So that is really process and going in the direction of having European data centers running on RISC-V, European cars. There is a lot of happening. For example, Seagate recently announced hard disk controller Of course, there was already Western Digital, but now also Seagate coming. So there is more and more collaborations. Greenwaves from France also has announced a new processor based on RISC-V, several RISC-V cores inside ultra low power. Yeah. In China, Alibaba is working on RISC-V for his cloud and edge servers. Technical University of Munich, the research team is working on RISC-V, putting it in a quantum crypto chip. Later, we also will have a talk from Andreas going in this direction. Sci-Fi has announced a RISC-V. Micromagic has a very fast 64-bit RISC-V. So there are a lot of industry players who are going in the direction of RISC-V and contributing. The community of RISC-V is growing. That is also a very cool thing because we have individual advocates. So that is people who are working from home who are interested and want to contribute. But we're also seeing that professional people who are making SoCs or IPs are joining this. We have fabs joining it, people from the software environment, so companies joining it, but also very important industry players which are working in high performance computing, automotive, cloud or mobile joining it. And of course, a lot of universities and researchers. And recently what we see is there are more and more investors. So you read in the news, for example, Sci-Fi recently had another round, $175 million US. So RISC-V is now really also some major technology where people believe in the future and put their money and say, yes, that will grow and there is a big, bright future. That is actually very interesting because it shows how RISC-V adoption is growing. When we started, we had quite a few people, but now we have over 2,000 individual contributors. We have over 104 chip companies. There are several service companies, software companies, of course, research. So the membership of RISC-V is really growing and keep growing. That also shows the interest, not only from industrial or research, but also from individuals who are interested in making RISC-V, making their own core for research, or just also looking for bringing it somewhere in the community. Another thing I want to point out, which is coming, that is still under work, so you can find more information at wiki.riscv.org display tech. So there are some technical programs. It's like a compatibility program where you can test your RISC-V integration and you can kind of slap this logo on it and say, yes, we are RISC-V compatible. I believe that will be very interesting for the future because we will have like other legacy architectures. We will have a way where we can say, yes, that is RISC-V compatible. And that is also something where my core, my company's core is compatible to this. That will enable also the software with the logo. You can be sure your software is running there. So I think this logos, which is still now under development, the program, the logo and everything will also help to boost and make the ecosystem more mature. The RISC-V is a community, so we have individuals, we have companies, universities, there are public institutions, but also nations. For example, India, Pakistan, they all have declared RISC-V their national instruction set architecture. So this sees how it's driving globally and how RISC-V is really getting traction. And yeah, from RISC-V, we hope you build it into your company strategy and maybe, like me, into your personal mission. Okay, so that was just an overview. I wanted to highlight how RISC-V is growing, how RISC-V is getting more strong. And now I would like to hand over to Alexander from Fraunhofer ASIC. And I'm looking forward for the presentation about the industrial the security from Andreas. Andreas, feel free to share your screen.
Okay, so thank you, Florian, for the introduction. And let me quickly you as well, so you can see me. So hello, everyone. My name is Andreas. I'm from Fraunhofer AISEC. We are located in Garching, near Munich. And today I'm going to talk about an authentication token, integrated circuit, based on the OpenTitan project. So the OpenTitan project is a project that is based on RISC-V. And for this reason, yeah, okay, it's okay. Let me quickly give you an overview of how we at our institute see RISC-V. So first of all, what we value is the collaboration behind it. We like the idea that it is an instruction set architecture that is shaped by many people around the world. We also like that it very often goes hand in hand with open source, and we think within this transparency there lies a lot of positive things when it comes to trust, to accessibility, but also to collaboration. So that's one. So two aspects that we like about it. We also think that RISC-V has the ability to strengthen the trustworthiness within our electronics. So if you think of a chip that we build that is based on RISC-V, we have a rather good feeling about the quality, about the specification, and ultimately also about the security that is that lies within this electronic device. So we think this is something that can help us, and this leads us ultimately also to an improvement in technological sovereignty, meaning that with RISC-V we have the possibility to increase the availability of microelectronic products, and to some extent better handle these critical dependencies that we many points have today. So this is a very brief introduction in how we see RISC-V, and with this I dive into the authentication token. Let me give you a bit of a motivation. Passwords are problematic for authentication. In many cases, they are reused, they're inadequately stored and handled, and in many cases are chosen by humans with low entropy. So using a second factor for authentication is a good idea. It's very often recommended. Many services already do it. And luckily we have worldwide standards that help us. We have the FIDO Alliance, we have the protocols and the standards from there. And we also have a range of products already. So we have closed source products and we also have open source products. And open source products very often are based on general purpose off-the-shelf microcontrollers and hardware and open source firmware. And in the past, we analyzed a lot of those products. This was a research effort of ours, and we analyzed their security, and we found some problems, but in general, they also make good efforts to provide a good level of security. This research sort of led us to the question: so how can we maybe design our own second factor authentication token? So how can we build our own authentication token? And this led us to the OpenTitan project, which is exactly built and oriented in that direction. So it's a project initiated by many well-known partners. It is a system on chip that has two main use cases: authentication and platform integrity. Authentication is exactly the use case that we need. So it is intended to be built as an authentication token. And it is based on an IBEX 32-bit RISC-V core. And as you can see on the right in the picture, it already has all the system components, the peripherals that you need for it to function as a system on chip. It also already has a lot of cryptographic hardware and in general a very great effort to achieve a good level of security. So these are a lot of things we appreciate. And so we said, okay, we want to base our own authentication token on this project. Our intention is sort of to take the project, to make some modification, and to manufacture our own integrated circuit and to build sort of a prototype for an authentication token. And this is why we, over the time, made some modifications to the OpenTitan project. Each of those modifications I will quickly discuss in the later slides. But in general, we have 4 points. So we, as you saw on the last slide, the OpenTitan itself has an on-chip flash module, which is used to store, for instance, secret data like cryptographic keys. We thought for manufacturing, especially if you go down to small technology nodes, or if you want to integrate the OpenTitan in an existing system on chip, this is a bit of a limitation. It's costly and it limits you to only a certain number of fabrication sites. So for us, it was a lot easier to simply remove the flash internally and move it outside of the chip, so use an external flash. Then we modified the secure boot a little bit. So secure boot is a concept that is already integrated into the OpenTitan world, but we added a post-quantum cryptography scheme to it, as we think this is a timely thing to do. It's a good thing to do right now. And then we have some security improvements also in the direction of isolating cryptographic keys and improving the debug module of the chip. So let me quickly walk you through those modifications a bit more. Removing the internal flash means that we have to store the secrets that we need. So we need secrets, we need cryptographic keys for our FIDO protocols. We need to store them on the chip somewhere. And we use 2 directions for this. So one direction is using one-time programmable bits, OTP bits. And the other direction is deriving the secrets that we need from a physically unclonable function. So that's a hardware structure that uses manufacturing variances to derive a unique key on each device. So this is the alternative that we are using. Of course, we still need an external flash to store our firmware, to store a bit of data that we need, for instance, for our puff structures. But in general, this is a viable solution. Everything we load, of course, from external to internal SRAM, for instance, we have to check for integrity and authenticity. But this is something that we can handle. So it is possible to do this. It opens up some new points of attacks, of course. So we have our OTP structure, we have our puff structure, we have a bit different access and bus transfers going on with the secrets. And of course, we have to check everything we load from external flash for integrity and authenticity. So these are new points of attacks that we introduce, but we also gain a lot from it. There are also a few shortcuts that we do, just for your information. The OpenTitan has a notion of ownership transfer, meaning someone, for instance, a company that produces second factor authentication tokens. Sorry, I think there is a microphone. Still
no problem, I muted. Sorry.
So the notion of, okay, no problem. So the notion of ownership transfer, this is something that the OpenTitan has in its lifecycle model, and what it means is that a owner, so for instance, a company that produces second factor authentication tokens, can claim ownership by installing cryptographic material into the chip, and this helps, or this is the basis for signed software that is running on the system, or for attestation, which is done later on. And of course, we are using our OTP structures for this, and for this reason, it's not possible to change this ownership, which we think is not a big disadvantage in our use case. Second thing would be if we implement downgrade protection for our firmware, we also have to rely on these OTP bits, and this limits us a little bit in the flexibility of this protection. So this was the wrap up of the flash removal. Then let's move on to the secure boot. So with quantum computers on the horizon, we have a couple of algorithms that threaten the cryptographic schemes that we have today. This means we have to move to new cryptographic primitives. And for secure boot, we think stateful hash-based signature schemes are a good and practical choice. So one of those is the Leiden-Micali signature scheme, LMS, and we chose it for implementation on the OpenTitan. So these hash-based signature schemes are based on the pre-image resistance of cryptographic hash functions, which is a well understood problem, which is why we are confidently using them today. And this LMS is a few-time signature scheme, meaning that you create a finite number of key pairs, public and private, and you can use those key pairs only once. So you are limited in the number of signatures that you can generate and verify. And this means that you can only do a finite number of updates on your OpenTitan. But this number can be increased to a level where we think it's very practical. Other than that, key sizes are very comparable to public key cryptography as we know it today. What we did with LMS then is we wrote a Rust implementation of it. We made sure that we do a safe implementation, and we maintain compatibility with the Rust crypto API. So this is an API where you can use a fixed set of function calls to do signatures, to create, so to sign something and to verify something. And with this Rust implementation, this is something, by the way, that this is open source. You can download it from our GitHub page, or it's also a Rust crate that you can use. And with this implementation, we saw that it's a bit slow. We spend a lot of time in those hash functions, which naturally led us to a hardware accelerator that we implemented for the OpenTitan. So it's an LMS accelerator that attaches to the SHA-256 core, and that significantly reduces the time to do LMS signature verification. Of course, it costs something, so it's about 20% size increase of the SHA-256 core. And if you take a look at the figure. There we see the speed improvement that this hardware acceleration brings. So compared to the pure Rust implementation, our LMS accelerator reduces the runtime to under 2%. What does this mean in practice? If we choose some practical parameters of the LMS scheme, then we can do a signature verification in about 10 milliseconds on the OpenTitan, which we think is a practical value. The parameters that we chose have an impact, and the impact is that the signature size is quite big. Yeah, so it's 1.6 kilobytes. But this is still a size that we can handle on the OpenTitan with our firmware. But it's something to keep in mind. So it's a big signature. And the number of signatures that I mentioned before would be 30,000 signatures, which is in our understanding more than enough for an authentication token and its life cycle. Let's go on to the key isolation. So a brief motivation is the firmware running on the IBEX is something that we do not fully trust because we know that mistakes in the development will be made. So this is natural, and it is very often exploited in attacks on devices. So we have a firmware and it's always buggy. And we do not want so an exploited bug in our firmware to lead to a full compromise of all the cryptographic keys that we have on the device. So what we want to do is we want to handle all key material separated from the IBEX core entirely in hardware. And what you see in the picture is the key manager highlighted. So this is the module that will take some root secrets and derive all the key material we need for our FIDO protocols. And we see the OpenTitan Big Number Accelerator, OTPN in short. And this would be the, it's a second dedicated RISC-V core with a firmware, so you can program it. And who's programming it is the IBEX. So the IBEX is writing firmware onto the OTPN. And how we implemented it now is that during startup, the bootloader loads the firmware into the OTPN, and then it locks the OTPN. So locking is simply a register that is written to, and this lock has the effect that no one, so not even a faulty firmware on the IBEX core, can change the firmware until a reset is done. And only if this lock is activated, then the key manager provides access to the keys, and the OTPN can use them. So this is sort of a further isolation of the keys on the OpenTitan. Last modification is the debug module. So currently the OpenTitan only supports a permanent disable of the debug module. What we want to have is a debug module that we can open and enable later on during the life of the token. So we took the pipe debug module and we implemented an authentication interface that is compliant to the RISC-V debug specification. And we made it modular such that you can do different types of authentication. And currently we have password-based and challenge response protocol implemented. And with this design, you can simply use whatever debugger you have, OpenOCD, for instance, and simply debug the OpenTitan in a secure way without permanently disabling the debug interface. So I've talked a lot about modifications that we did to the OpenTitan project. So these modifications are to a great extent done, tested, and working. And what we want to do, what I mentioned earlier in the talk, is we want to manufacture the IC. So we want to manufacture an OpenTitan IC, and then we want to test it. So what we mean by tested is we want to do a security evaluation. So security is a big topic within the OpenTitan. And the ICs that we are manufacturing, we want to analyze them once we have them in our laboratory. So we have a set of analysis and attack techniques in our lab. So power and the M-based side channel analysis, fault injection, glitching, and in the near future we also have some more invasive analysis techniques like laser voltage probing or thermal laser stimulation, which is especially nice for on-chip memory, for reading out on-chip memory. And with these techniques, we want to assess the security of the OpenTitan project in general, so everything that is already there, cryptographic accelerators, for instance, and of course we want to assess the modifications that we did to the OpenTitan project. Yeah, so we have a lot of analysis targets. We have not only the cryptographic accelerators, we have bus transfers, we have a lot of critical operations during secure boot, for instance. We have our OTP and PUF structures, and we have our SRAM content. So there's a lot of attack targets and points that we want to analyze. Good. This already brings me to the end of the talk. So what we want to do is, our plan is to build a trusted microcontroller for second factor authentication. We want it to be RISC-V based, open source, and secure. All of which is by design part of the OpenTitan project. So we think that's a perfect fit here. We did some modifications to the OpenTitan. We removed the on-chip flash. We added a post-quantum cryptography scheme to secure boot, improved the key isolation and the debugging. And our plan ahead is to manufacture 2 generations of the chip. One this year in a slightly older technology, and one probably in 2 years in a modern technology node. And based on all the evaluation that we will have in the future, we will definitely look into certification. So is it possible, and to what extent is it possible to do a security certification for the OpenTitan? For instance, a common criteria certification. And we will also closely monitor open source process design kits like Skywater, because we think can be an exciting combination to use with our project and our work. So that's everything from my side. I thank you for your attention, and I'm happy to answer any questions.
Yeah, I see first question from Arthur. Arthur is asking,
there's one
if
question in the
experience
chat,
any difficulties customizing OpenTitan. Yes.
So thank you for the question. Difficulties I'm thinking, so in what respect do you mean difficulties? So difficulties working on the project, difficulties making an own chip, or maybe you can specify some more information here. Okay, making a chip. So I would say, in general, we don't have like severe difficulties. I mean, there are some aspects I think that are a bit different from an IC development that is not based on an open source project. So the OpenTitan is a project where there is active development. So there's a team from low risk, for instance, who are, as we speak, actively developing and testing and verifying the OpenTitan further and further. So it's a living project, and we have to keep up to date with it. So this is definitely one challenge. So maybe next week or in 2 weeks, there is again a big change in the project, or some modules have matured, have changed a little bit, and so on. So we have to constantly sort of be up to date and keep track of whatever is going on in the project. I think this is a bit this is a bit difficult, you might say. Also, different modules within the project have different levels of maturity. So in the past, there were several peripheral modules in the project that were simply not working, so we couldn't use them for our development, for our testing, and so on and so forth. So I think this creates a bit of an additional dependency on the project there, because it affects the verification, it affects the testing that you are doing. And we were constantly having discussions of which modules to use, which maybe to replace, etc., etc. But I think other than that, if you put in the time and effort and push the modules that are within OpenTitan to a mature level, from that point onwards, I think it's not too different from any other IC manufacturing. Does this answer your question? Very good. So there's another question in the chat. Yeah. Is the OTBN also another IBEX core? To be honest, I don't know for sure if they have a stripped down IBEX core on there, or if it's another core, but I can check that. I don't want to give a wrong answer here. This is maybe something that is something I can provide in later on or within an email. And the programming of the OTBN, can the firmware be modified in the first untrusted core without seeing it? So I don't know if I understood the question correctly. Could you maybe rephrase it?
Maybe I switch shortly on my microphone. So if I understand it, the first IBEX core is taking the firmware and writing the firmware to the second core and then locking the second core, and the second core start working. So when the first core, the untrusted core, write the firmware, how do you protect the firmware so that it's not modified, or that there is someone manipulating this firmware for the trusted core? That is my question.
Yeah, so thanks for the question. So the process is as follows. So the IBEX itself, so the IBEX core, the main core is still the core that boots up. So the bootloader is running on the IBEX core, and the improvement that we see, so the reason why we did it is, so the bootloader itself is more, is something that we have under much better control than the rest of the firmware. And this is why so our concept is that we have a secure boot chain. So our bootloader is verified by a ROM bootloader, so that is burned into the IC itself. So we have this bootloader. This is more, this is sort of part of the secure boot chain, and this is the part that installs the firmware into the OTBN. So this is the kind of software that we trust. Of course, the bootloader, if it's not trusted, if it's not signed or part of secure boot, of course, it could do anything. Yeah? If it's possible to manipulate the bootloader, it could install any firmware into the OTPN, also a malicious one. But as we build the system, so this is the part that we trust. And this bootloader installs the firmware and locks it. And only afterwards, the firmware, the main firmware is executed. And this bigger blob of software, this is something that we think, this is something that we have under less control. And this is where we think the probability is higher that we introduce a bug in the software that might be exploitable. So does this answer your question? Okay, then we have some more questions, I think. So one from Clemens. Did you do any pre-silicon security analysis in the design or rely on the Titan design? So what we are doing is we are doing FPGA pre-silicon verification, but we are not using, for instance, our FPGA setup, our FPGA prototype for security analysis. Yeah, so we are not doing a power or AM-based side channel attacks, for instance. Two reasons maybe. So first reason is that the OpenTitan by design has a lot of reasonable security features in there. And it's so fair to believe that these security features have a good effect on the resistance, for instance, against side channel attacks. So this is not something that we evaluate right now, but we definitely will evaluate in the ASIC that we are building. And the second thing would be the transferability. So usually, if you do power and side channel AM and power-based side channel attacks, the results do not directly transfer between FPGA and ASIC. So what we will focus on is the ASIC side of things. Does this answer your question? Very good. And then we have another question, I think. Okay, I don't know if it's a question or a remark from Akira, but I understood it as a remark, I think. So please tell me otherwise. Very good. Are there any other questions? So there's another question from Simon. So do you know if the OpenTitan security model can be mapped to ARM PSA such that a PSA certification is possible? That is a very good question, and unfortunately, I do not know. So we haven't looked into that one. But this is something I will definitely take from today. So yeah, if you're interested in that, feel free to write me an email, drop me a line, and we can discuss that further. But that's a very good remark. I will take that with me. Good. Any other questions?
Sounds like we don't have any more questions. So thank you very much, Andreas. That was a
Seems to
really
be it for now, I
interesting
think.
talk. Yeah, I could learn a lot about the OpenTitan itself, like Akira said, but also about how you're doing it for the quantum proof. So that is very interesting. Thank you very much for taking the time and being here today on the RISC-V. It was definitely super interesting.
Sure, thanks for having me.
Okay, then thank you, Andreas, and hope to see you soon again, especially when you have tape out your chip, when you have some of the power analysis. I saw the cool picture of the chip, which you kind of had decapped. So I'm hoping to see this with your chip, maybe in 1 year or 2 years. It would be extremely cool if you can come back and share with us what you're doing, if it's possible. And again, thank you very much. Okay, then today we have one more talk. This talk would be by me. I would like to go about RISC-V goes big. So I would like to share some impression why I think RISC-V is now coming to the industry, why RISC-V has the momentum, and why we will see so much more in RISC-V. This talk will a little bit be centric on Andis Technology. That's the company I'm working for if I'm not just busy as a RISC-V ambassador. Andis itself, we are doing RISC-V course, and I want to share a little bit what we are seeing, where the direction goes. So what we are seeing from a commercial RISC-V supplier, we are seeing kind of 5 directions where RISC-V is really getting strong. The first one is the mobile area in mobile phones, so in hotspots like Bluetooth, Wi-Fi, but also touch screens. There is a lot of RISC-V adoption. There is the microcontroller market. There are big names, for example, like Renesas, who recently has announced they have some RISC-V now running Linux. But we also see that the AI market has more and more adoption. We are talking about data center or cloud solutions where accelerator chips are used, built on RISC-V with vector processor. And then also 5G is having more adoption for RISC-V. There are also from these companies like Picocom has shared a little bit what they are doing publicly. If you go on their webpage, you find a online talk from, I think, last year, where they share their architecture and how they use RISC-V inside. HQ 5G application has shared what they are doing. So we are seeing the flexibility of RISC-V and the possibility to add custom extension, really accelerating not only AI, but also the 5G. And then last but not least, also storage. We see a huge demand for 5G. I mean, big companies like Western Digital has announced they want to switch completely to RISC-V, shipping billions of RISC-V cores. Seagate, earlier in the RISC-V overview, I have shown that they also announced the RISC-V product. So there is really big industrial adoption. Renesas itself, they make some application-specific microcontrollers. So that is cool because it means it's off-the-shelf microcontrollers. In other words, you can go to one of your big favorite distributors, Mouser, DGK, Arrow, and you can buy this CPU and you can make your own PCB with a RISC-V CPU. So the cool thing is, because Renesas is one of the biggest player in this market, that really brings RISC-V to a lot of people and give access to a lot of people. Picocom, working on 5G, is also a very interesting company. They are using actually clusters of RISC-V. So they have 2 clusters, each has 16 cores, each connected over a bus matrix. And these clusters are really working on doing the packaging, the receiving package, checking, adding headers and so on, offloading partly the main CPU. The second cool thing is that this is an open RAN, so that is really driving the open standard where you are not locked into one vendor, for example, one of the big vendors providing all the infrastructure, but where you have a defined architecture, defined interfaces, and you can write open source, open software and interacting more of these cards together. So that is also something, the same idea like RISC-V driven by them. Then HP Micros, they also have made available a core. They are comparing this RISC-V core actually to ARM M7. It runs a little faster, but here you also have a 1 GHz core. What you can see is that RISC-V really can have a high performance boost compared to, for example, ARM. This HP Micro has also talked with Seeger making really great IDEs for a lot of microcontroller, a lot of people using them. I also use them for some side projects. The cool thing is that HP Micro has made some agreement with Seeger, and you can use the Seeger IDE for free to program this microcontroller. And the next cool thing is that, of course, you also have the open source operating systems like FreeRTOS, Zephyr, and many others, which are already as a BSP ready ported to this. That means they have all the basic information about the CPU. That is, we believe, also accelerating the adoption of the market. And then we're now also starting to see Linux. Of course, we already had Linux ready chips. Sci5 has one of the first chips on the market, pretty cool. Microchip, the FPGA maker, or has also a FPGA with RISC-V on the market. What is now with Renesas pretty cool is that it's a general purpose microprocessor unit. So you can buy this off the shelf, you can make your own design running Linux. So I think that is also a clear sign that RISC-V has arrived, and RISC-V is becoming more and more the standard and accepted solution in the community. So that's why I think RISC-V is going big. RISC-V since 2015 is continuously growing. It has started from small microcontrollers, and now we are seeing it in, I would say, small Linux cores. We have a lot of development ongoing in the industry to bring it also to the high performance Linux cores. In the beginning, it was very focused. So RISC-V has been focused on the AI usage, but we are now seeing that it also comes to standard microcontrollers, microprocessors running Linux, which means there is a lot of different people making different things using RISC-V, and seeing that RISC-V is now used by big companies for this means they have the confidence that they know there is the good support, there is a big community behind, and it makes sense. So there's also some more things to see. RISC-V is going back big. One of it is this generic use cases I just mentioned with the general purpose microcontrollers, but there is more industrial adoption. So we see that customers making really rugged industrial devices adopting RISC-V. And recently, if you're following RISC-V, you will see there is a lot of information updates about automotive. So automotive, very secure, self-driving cars. Think about this. You cannot have any problem if these people start adopting RISC-V. It is, from my personal point of view, really a sign that RISC-V is going big and is kind of unstoppable. Now, who is Andis? What is a commercial RISC-V IP supplier anyhow? Andis itself, we are a public company, so we are 17 years old. We are traded on the stock exchange in Taiwan. And Andis is focusing on CPU IP only. So we make the CPU IP, We verify it, we bring the support, we are updating if there is something in the RISC-V specification. That is our main business. But next to this, we are also very active in the RISC-V. So we are a founding member of the RISC-V International, and we are engaging heavily. So for example, I'm a RISC-V ambassador, but we also have different people from us. We are working in the task groups and so on, and bringing our ideas about RISC-V, seeing what is needed in the industry and bringing this feedback from the industry to the RISC-V. And last but not least, we are also a major open source contributor and maintainer. That means we are really making our own CPU core, but then we are also helping to port like OpenSPI, U-boots. That's where you find our guys contributing, but also to the Linux kernel, where we really try to help with the community together to make things, to improve things, and bring also our manpower inside. Andis itself, we are 17 years in business. There are over 250 commercial licensees who are using this course from us. And we have shipped now in total accumulated over 10 billion cores. Andis itself located in Taiwan. Taiwan is here next to China. We are also in China, Korea, and Japan. We do have offices in the United States. We are represented in the Netherlands, France, and we also have sales representatives in Israel. One side note, if you want to work for us, we are looking like many of the big RISC-V manufacturers for people. So feel free to apply for a job if you want to design RISC-V cores for a living, if you want to verify them or work in tech support for RISC-V. There are a lot of job openings worldwide, for example, with us, but of course also with other RISC-V manufacturers. The story how Andis started, I don't want to go into the details. 17 years old. Basically in 2015, when RISC-V came around, we had a close look. We saw that this is very similar to our own architecture. We had our own in-house RISC architecture. We called ANDISTAR v3, and we decided for the future, RISC-V will be the future, and we switched our future development all for RISC-V. Our first core announced in 2017, so you can see it takes some time to develop a solid RISC-V core. And then 2018, 1 billion cores shipped in 1 year, 2020, 2 billion shipped. It is kind of accelerating. What is the added value a commercial RISC-V supplier is bringing to RISC-V? So there are a lot of different values, of course, we are bringing. One of the values is the architecture. As RISC-V is the instruction set architecture, which is open, you have different ways how to implement the architecture of your RISC-V. And you have great open source like the IBEX core Andreas mentioned before, they're using in their OpenTitan derivate. Andis has their own architecture. That's where we have our know-how and where we are contributing to make this better. We also have something like a feature we call codance, which can reduce the code size. RISC-V itself already has the C extension for compressed code, and then Andis itself has another extension we call codance, which can further help to reduce the code size. For industrial use, very interesting because it can save a lot of memory. There are also things like power breaks, stack save, and we are also working together with the RISC-V on some vectored platform level interrupt controller to make a more preemptive behavior and make it usable in like machine controls or motor controls. And this also has helped, for example, for the DSP extension. So the DSP extension was actually contributed by Andis. We have developed this in-house for our own RISC architecture previously. So that is industrial proven, that is used already. And when RISC-V came around in the beginning, there was the vector extension, which is pretty cool, which is really powerful. But that's also the point. If it's really powerful, it also needs more area, more space in your IC. And we saw that this DSP extension can save space, can make the programming a little bit more easier. And if you're looking on some accelerations, so if you do some keyword spotting like wake word detection to wake up the main CPU and then do the processing or do the analyzing of the sentence, you can speed this up with the DXP extension by more than 5 times. And like an image detection, you could speed up almost by 9 times. The speed ups also mean you can have a lot of power saving. And so Andreas was working to introduce the DSP extension to RISC-V to help to write this spec. And now we are also trying to finalize it and push it to get it ratified. And this custom extension, that's another cool thing from RISC-V to have this DSA, domain-specific architecture, which really let you add your own custom instructions. To have a custom instruction is a cool thing, and everyone can basically do it, but it takes time. So in this, we have this kind of tool, which is a little bit like an EDA tool where you add your custom instruction via Verilog defined code, and then our tool, we call it Copilot, will generate extended RTL, bind it with the CPU RTL, generate the extended instruction set simulator, and also the extended tools like compiler, disassembler, and so on. So that is one of the added value a commercial vendor can bring to companies who want to design an ASIC. Last but not least, automotive is very important. So Andreas itself, we are working on automotive. We are having the first core already ready. That is a core which is ASIL-B ready. You can drop it in. So of course, also other people working on this. But the cool thing is, if you're in industry, if you want to design with automotive, then you kind of need someone who help you, someone who do all this verification. And that's sometimes not so easy for open source. Maybe we will see this in the future. But at this moment, there are still a lot of calculations, manpower behind. So that's where a commercial IP supplier really can have some feedback or help to contribute. The roadmap, what Andreas is offering, we are ranging from small cores. We call this internally our M22. So that is available as RV32E or RV32I, 16 general purpose registers or 32. It's a 2-stage core in 28 nanometer HPC plus. We have up to 700 megahertz worst case frequency. Our 25 series ranges from small embedded cores over the data processing, where you have the DSP, up to an application processor where we add a memory management unit, and last but not least to a multi-core where you have L1 and I/O coherence and optional L2 cache. Then the 27 series, here we have a feature called Memory Boost, which is accessing or speeding up the memory access and enhance the throughput. That's also where we have our vector processor, 512-bit wide vector processor, can work on a lot of data. And then last but not least, our 45 series, again, from embedded control up to the multiprocessing. The 45 series is a dual issue, so a superscalar design, 8-stage pipeline. And basically that's what Andreas is providing to customers to license. So companies, for example, Renesas is one of our customers. They have this 45 and they can license this CPU IP, which is tested, verified by Andreas, and then put it in their own SoC, add all these other features and make a great lineup. So that is one of the contributions a commercial IP supplier can bring. Just to give you a very quick overview, very brief about how it looks inside of one of the CPUs. So I don't want to go into all the details, but I thought the 45 series might be interesting. So the baseline is the RISC-V, and it's available in 32-bit or 64-bit. Then you have the G, which is the IMAC. You have the C and the N profile, and you of course have this ANDIS extensions I mentioned before, which are compatible with RISC-V, like Codance, stack safe, and things like this. So we have the base processor, which is here. So we are adding the P extension, or we are also adding the memory management unit if you want to run a Linux, and we have the same for multiprocessor. The 45 is an 8-stage in-order dual issue. There are 2 ALUs inside. And then we are also supporting like the memory boost I have mentioned before, and low power dynamic branch prediction. Things like this. Branch prediction is something kind of critical where you really can save power, and if implemented in the right way, you also can speed up your kind of program behavior. This 45 series we are offering for customers also in a multi-cache environment. So then it's kind of pre-integrated. You have a coherence manager, which is managing the I/O and L1 coherence between different cores. We are supporting up to 4 cores right now. There is additionally an L2 cache controller up to 2 megabit. And then the bus interface is kind of standard. So you have the AXI 128. You have slave ports for the coherence manager, and for your local memories, you also have slave ports, so you can write them before you are releasing the core from the reset. You also have the JTAG ports for debugging, and that is all kind of pre-integrated, so customers can license it and kind of drop it in their design, adding their ASA IP to make one ASIC or one chip you can buy off the shelf. That is also some kind of platform. So the core, that's what I just introduced right now. And then we are also offering some kind of bus metrics with some generic IOs, some generic DMA, direct memory access. That is really to allow customers who want to develop a ASIC to have some starting point and to concentrate on their third party, adding their third party, and help them with the time to market, and also help them with the RISC-V to have an expert who can provide the right core for them. The vector processor, I think, is quite cool because the vector processor enables a lot of data throughput in RISC-V. And this here has a 5-stage scalar CPU, which we have bundled with our vector processor. It is supporting the standard formats of the RISC-V vector, but ANDIS also has added enhanced formats like bfloat16 or int4, quite important for a lot of neural networks. bfloat16 from Google, for example, BrainFloat, is now very common. The processor itself, you have your scalar core, and then the vector processing unit is kind of added to the scalar core. What is interesting is that this vector processor unit has 2 ways to load data. So you have normally your RISC-V load store pass, and then ANDIS has added a second pass over custom extensions or custom specific instructions where you can load data directly without going through the scalar core, therefore saving some bandwidth for the core itself. That's the memory passes I just mentioned. The streaming ports, that's how we call it, where you can get, for example, you can bundle it with a hardware engine or a smart memory directly, and then the vector processing unit can load the data directly from here without going through the bus interface of the scalar core. That can save a lot of bandwidth, that can help you to bundle something, for example, like a neural network engine or kind of hardware engine directly to the core, also saving a lot of latency instead of going over the bus. And that means not only latency, but also power if you can save this bus rides. The RISC-V environment is something Andreas is also working on. So here we provide our own IDE, I would say. This IDE has a lot of things inside, optimized tool chains, profiling and analysis capabilities. And then we also add a software stack. So we have, of course, different operating systems like FreeRTOS, but there are also drivers for our IOs, which our customers can use. Of course, all the open source software is also available on our public GitHub because we are leveraging the open source. We also make it available for the open source community, and we also try to contribute and port it back to RISC-V itself, to the open source community. We offer some kind of virtual SoC, so our customers, for example, can write their software inside our IDE with our drivers, with the BSPs based on the open source, and then simulate it in the virtual SoC. That is already good to start your software development before you have a chip. And then in a second stage, when you have your RTL almost ready, we have FPGA boards where our customers then can debug and trace in the FPGA boards to get a real behavior, to get it really cycle accurate. We are working on an ecosystem. That means Andreas is partnering up with a lot of people. For example, if we are looking on the development tools, IR, Seger, Ultrasoc, Imperas, Lauterbach, just some of our good partners which are supporting our Andreas core. If you're looking for software and IP, we are working with a lot of different people, and also in the security side, you see companies from America, Europe, but also from Asia. So our goal is really to bring all this together and to offer the customers who are licensing a commercial IP from Andreas, for example, to have whatever flavors they need ready, tested, and available to run on our cores. And that is also when you go for a commercial supplier, one of the benefits, this kind of partnership. I mean, there are a lot of great open source, and that's a great start, don't get me wrong. But sometimes maybe it is limited resources. The developers only can support a certain amount of projects. And then with a commercial supplier, that's where you can have more manpower, which is bundled, and have more different options available. So just to wrap it up, Andreas itself, we are an IP provider. Totally over 10 billion cores shipped, 17-year-old. We are working in the automotive area, so we are certified ISO 26262. And we are having cores from very small microcontroller units up to powerful vector units, from a single core up to a multiprocessor. And we are, believe RISC-V is going big. So if you want to license a core, feel free to talk with us. Okay, that was my introduction about RISC-V. Do you have any questions? I'm looking in the chat. Seems like no questions so far. If there are no questions, I would say thank you very much.
I have a question.
Yes, please, Andreas.
Yeah, Florian, I have a question if I may ask.
Yes, sure.
Yeah, so thank you for that overview. And my question would be regarding open source EDA tools. So you mentioned EDA tools, of course. The company of your size is heavily relying on EDA tools for the IC design. And my question would be if you have any thoughts on the open source EDA tools that over the past years have grown a little bit, I would say, and whether they at some point be also an option for you to go or to use them in your IC design flow.
That is a very good question. We are looking for these EDA tools, the open source EDA tools, very closely, especially the efforts from the FOSSI Foundation. And Andreas, you also mentioned it in your slides, the Skywater OpenPDK, which is also leveraging a lot of this open source EDA tools. That is a great way. Personally, I believe that will be big step in the future that will really be able to use it from a commercial point of view. At this moment, it's not ready yet. So there are still some hurdles to overcome. PDKs is one thing, so more vendors would need to make their PDKs open source, which would be necessary. And then we will need to see how that is accelerating. But from the development I'm seeing, I really think it's going into the right direction. And I believe we will have more and more coming in the future, but need to see where we are going here. So making it short, conclusion, OpenEDA will come. At the moment, I think it's not ready yet, or it's not only I think what I'm seeing, it is not ready yet for a real commercial IC design, but there is a great effort and I think it's going in the right direction. So in the future years, it will be definitely ready to use. I hope that could answer your question, Andreas.
Okay, thank you.
I see one more question from Axel. Axel is asking for the SEL4.
Absolutely.
So
thank you very much.
The security. We are having designs based on the SEL4 for the security. So that is something on the commercial point which we are providing. If you're interested in this, feel free to contact me. We are working here with partners together, so it's not coming from Andes. We are depending on partners to make this happen, but it's definitely possible. Okay, are there any other questions? If no questions, I would say thank you for your time. Thanks everyone for joining. Again, sorry for the hiccup with the Zoom in the beginning. So I hope I will make this better in the next time, so you can blame me for the Zoom hiccups this morning. Sorry for everyone who has to watch it online and couldn't join, could not have his opinion. If you have some topic you would like to talk about RISC-V, if you have some cool project, open source project, or also if you're a company working on RISC-V, please feel free to contact me. You can contact me at my work email. Frankly speaking, I use the work email also for my RISC-V ambassador things. So feel free to contact me at florian@andestech.com. I hope to have another meeting or another meetup in Munich, maybe in 3 months. And I'm still looking for context or speaks. So please feel free to contact us. In the chat, I see one remark from Akira. Akira Tsukamoto is my good friend, also RISC-V ambassador based in Japan. So today in Munich, we have our RISC-V Japan ambassador joining. Thank you very much, Akira. And Akira says he's hoping to have more development boards coming out with Linux-capable multi-core chips from Andes. Thank you, Akira. I also hope, or I also think there will be some new developments coming soon. In general, I think it's great to have RISC-V coming as a standard chip with Linux capability support. So we are talking about something like Raspberry Pi, similar development boards or Beagle boards. I think that really will help to accelerate RISC-V and bring it also to the high-end cores. And then who knows, in a few years, we can run our notebooks on RISC-V powered chips. I'm actually pretty sure we are going into this direction. Okay, so thank you everyone for joining today. Thank you for the people who joined from very far away from Japan, India. Thank you for the people who are joining from Munich directly. And please feel free to use the RISC-V platform. And we are looking forward to have your ideas, what we can present next time. If you don't have a talk, but you know, hey, there is some cool company working on something, I would like to know more about it, let me know. Then I try to contact them and see to work with them. For example, one of these 5G companies I'm in contact with right now who are using RISC-V, and I'm asking them to introduce what they are doing with RISC-V and why they choose RISC-V to get some understanding, also from the industrial side to understand why RISC-V is really driving, but of course also academic things are great. Okay, then thank you everyone, thank you for joining, and see you next time for the next meetup with RISC-V, and have a good evening. So talk to you soon. Bye.